So how are you?
I'm good. How are you?
All right.
No, I think like nothing new. Again, like last week I presented one project. There was one more project that we had presented in college last week, like this week. And then now we have our final theory exams from next week, so I'll be busy with that. So yeah,
Okay.
nothing new. I probably after exams I can look into something new, a new project, a new implementation, read more research papers.
That's good. Yeah. Yeah, thank you for your
How have you
presentation
been?
last week. Yeah.
Mhm. I didn't hear you. Sorry, I was asking and then you spoke. So,
Oh, okay.
can you repeat your question? Yeah.
Yeah, thank you for your presentation last week.
Yeah. Thank you.
Yeah. All right. Anything else or
No, nothing else. Yeah. Probably next week, like if I join the meet, I can show what we presented last week. It was an optimization techniques project that we used hybrid TLBO and PSO and tried out different algorithms on one problem statement to see which is the most optimal. I don't have it ready right now, otherwise I would have presented it. But probably next week I can show that.
okay.
Yeah,
That sounds good.
yeah,
Yeah, I'd like to see that.
yeah,
All right, yeah, so maybe you can present on some of your stuff next week, Vidhi. That'd be great.
yeah.
Yeah. So this week we're going to talk about NeurIPS and some of the things going on the next week and a half or so of their conference. And we're going to talk about some other things. I want to follow up on last week's presentation that was on evolution and large language models, like evolutionary approaches to like taking evolutionary programming and transferring it to the large language models arena. And they were I was disappointed in the methods that they used there because they didn't describe what they were doing. They basically said that you can use an evolutionary approach to kind of sort the output of large language models or something with the prompting. But then they said, this is better than constructing a fitness function, which is sort of the core aspect of an evolutionary algorithm or evolutionary computational technique. That you have a fitness function that evaluates every solution and basically promotes it based on fitness. And so they said they used prompts or something, and I couldn't figure out what they were trying to do. Because if they were trying to do something with like text and language and maybe semantic content, that would be really interesting. But I don't know if that's what they were doing or not. Anyways, it's all sort of proprietary because it's Google. And so I have another paper that someone put out that maybe clarifies some of that, maybe not. So we'll talk about that. So this past week we had one meeting. We had our DevoWorm meeting. I covered the book The Art of the Soluble by Peter Medawar, who was a Nobel Prize winner back in like 1960. And he took a bunch of books that had been published probably 100 years ago now, and he critiqued them. And it was really interesting, the critique. You go back to that meeting, you'll see what I mean. And then I talked a little bit more about On Growth and Form book by Darcy Thompson and how that all relates together. So check that meeting out on the YouTube channel for DevoWorm. Okay, so yeah, we're coming up on the end of the year. As you know, this is the last month of the year coming up. And that means that we're thinking about next year. So I wanted to make it clear that, we've got a lot of things that have to kind of happen right away. First of all, we have to maybe think about Google Summer of Code, think about what we want to do for next year, what we want to achieve. And so that requires planning, and that requires thinking about that now, and then maybe by January we can get off, hit the ground running, as they say. So, just think about that. I don't know if people want to do something particularly ambitious, or if they're just looking for a small project or whatever, but let me know. I'm also going to try to do a recap of the lab's activities for the year, publish that on YouTube, so you'll have that as well. I'm not sure what will happen because I've got a lot of things coming up towards the end of the year, and I try to do one every year. So, okay, yeah, I'd like to do GSOC again in 2026. Yeah, this is we'll probably do the open source sustainability project, and follow up on that. We did do the presentation that I did for the active inference symposium. That kind of goes over sort of a lot of the math that kind of connects between reinforcement learning and active inference, and that's maybe where we want to go to, into that area. So kind of connecting things somehow. I know it's kind of getting maybe separated from the practical aspects of the project, but I think that's useful because I think there's a lot to say about collective behavior in open source communities, and using open source communities as sort of a proxy for that. So we'll see what happens there. But yeah, if you have like an idea for a project or something, or how you think that things should happen, let me know. And we'll because in the years past, we like to invite people to take a wide range of approaches to the problem, not just kind of like something that I set out or that someone else sets out, but to kind of approach the problem and make it your own. So okay, and then of course I'll kind of go over some of the things we've done this year. A lot of things kind of get forgotten about, so we need to bring those back to the fore as well. So this coming week is NeurIPS 2025, and this is the website. This is the agenda. You notice that this year they have this tab. It says San Diego and Mexico City. So from my understanding, they're doing two versions of the conference, one in San Diego, one in Mexico City. They're doing this because of the visa problems we're having coming to the U.S. now. And, Mexico, of course, they could have held it in Tijuana. That might have been a little bit more integrated, but they are doing the second version of the conference in Mexico City for people who don't want to go into the U.S. And then, so they have the San Diego sessions, which are, I think, a lot of the bulk of the sessions and workshops. And then the Mexico City version, which has its own schedule and workshops. Not as many workshops, but still. And then I believe there's also a virtual component. So if you can't make, you don't want to pay for the whole registration, you can't make the meetings in person, you can catch up online. But anyways, this is I like to go over this because I like to see what people are doing in the field and kind of get a good, cast a wide net in terms of the types of topics that are being approached here. So, they have different panels, they have invited talks, and then, of course, they have their workshops, which are sometimes before the conference. And, I'll go through the list of workshops in a little bit, but let's just go through the agenda. So, of course, they have women in machine learning. They have multimodal data foundations for industry. They have this Expo Talk panel, Beyond Benchmarks, Rethinking Reasoning in Large Language Models. They have some things on synthetic data generation. They have different types of large language model discovery sessions. They have Latinx and AI. They have model merging, which is interesting. It's a tutorial. That is, we don't have any more information about this, but basically, this is model merging. theory, practice, and applications. There's human AI alignment, foundations, methods, practice, and challenges. There's new frontiers in hyperparameter optimization, which is interesting. It's always been an interesting problem because, people, that's kind of the secret sauce of a lot of models is tuning the hyperparameters and getting them optimized. Then they have planning in the era of language models. They have explain AI models, methods, and opportunities in explainable AI, data-centric AI, and mechanistic interoperability. They have LiDAR processing, more multimodal stuff. This is intro to generative computing, and mobile video diffusion transformers. And let's see, large language models power intelligent data engineering from workflow to design. Then this who needs attention anyway, elastic state models for real-time streaming tasks. That looks really interesting. That's a demonstration. As you know, there was this paper about 8 or 9 years ago now that said all you need is attention. That's the famous title. And now who needs attention anyway? As we move on, we always find that, I know there's some marketing in terms of like how people sell their own work, but like that's kind of an interesting take on, our progress. This is interesting, causal fairness, an open source Python library for causal fairness analysis. Let's see. Let's go up to this one here on Wednesday. So that was Tuesday, the 2nd of December. Wednesday, there's an invited talk by Rich Sutton, The Oak Architecture, A Vision of Superintelligence from Experience. And the abstract, as AI has become a huge industry, to an extent it's lost its way. What is needed to get us back on track to true intelligence? We need agents that learn continually. We need world models and planning. We need knowledge that is high level and learnable. We need to meta learn how to generalize. The Oak architecture is one answer to all these needs. It is a model-based reinforcement learning architecture with 3 special features. So number 1, all of its components learn continually. Number 2, each learned weight is a dedicated step size parameter that is meta-learned using online cross-validation. And then number 3, abstractions in state and time are continually created in a 5-step progression, feature construction, posing a subtask based on the feature, learning an option to solve the subtask, learning a model of the option, and planning using the options model, the FC stop progression, which is the this method that they have. The Oak architecture is rather meaty, In this talk, we give an outline and point to the many works, prior and contemporaneous, that are contributing to its overall vision of how superintelligence can arise from an agent's experience. So, interesting take on superintelligence from Rich Sutton. This is another talk, Yejin Choi, who is The Art of Artificial Reasoning, and the abstract here. Scaling laws suggest that more is more. Brute force scaling of data and compute lead to stronger AI capabilities. However, despite rapid progress on benchmarks, state-of-the-art models still exhibit jagged intelligence, indicating that current scaling approaches may have limitations in terms of sustainability and robustness. Hold that thought because we're going to talk about that in a little bit from this interview that Ilya Sutskever did with someone. So I'm going to kind of think about that a little bit. Additionally, while the volume of papers on arXiv continues to grow rapidly, our scientific understanding of artificial intelligence hasn't kept pace with engineering advances, and the current literature presents seemingly contradictory findings that can be difficult to reconcile. In this talk, I will discuss key insights into the strengths and limitations of large language models, examine when reinforcement learning succeeds or struggles in reasoning tasks, and explore methods for enhancing reasoning capabilities in smaller language models to help them close the gap against their larger counterparts in specific domains. So again, thinking about, just, this whole focus on scaling where they just make the models bigger and bigger. And, that's not necessarily leading us to something that's a very rich intelligence. It's just kind of a bigger intelligence. And those things don't kind of necessarily, match up. They don't meet the moment, as they say. So that's interesting. People are starting to think about that a little bit more, especially as you have bigger and bigger models that still have some of the same problems that the smaller models did. So this next talk is Kyung-Hoon Cho, From Benchmarks to Problems, a Perspective on Problem Finding in AI. And the abstract here. During the past 15 years or so, I have worked on a series of seemingly distinct but eventually related problems, including machine learning algorithms, generative modeling with neural networks, machine translation, language modeling, medical imaging, a bit of healthcare, protein modeling, and a bit of drug discovery. I chose to work on some of these problems intentionally. While it was pure serendipity that I worked on some others, it was only in hindsight that these seemingly different problems turned out to be closely related to each other from both technical, social, and personal perspectives. In this talk, I plan to do my own retrospective of my own choices, be them intentional or not, on these problems and share with you my thoughts on what our own discipline, which is sometimes called computer science, data science, machine learning, or artificial intelligence, is. That's kind of interesting, kind of a retrospective of the whole field and how it's evolved, especially since it moves so fast. It's hard to know kind of where we've been and think about that, because even with our lab, we have that problem where we're just kind of churning away and we're not necessarily putting things into some sort of sense making or order. I try to do that as much as possible, but even then it's hard to do, and especially in a fast moving field where results get buried pretty quickly under other results and things like that. So those are the invited talks. Then we have some other things down here. We have a bunch of sponsored content. We have Queer in AI. We have language model sessions, deep learning sessions, reinforcement state space sessions, generation simulation sessions. Let's see if we have the actual talks now. All this is recorded as registration, but that's okay. I just want to go over they have a theory session. They have the creative AI panel, design for intelligence, humans, machines, in nature and emergent co-creation. That looks interesting. Then this is something that I knew we were talking about last week. Morgan brought it up in terms of what people are interested in the tower. And we'll talk about a workshop that they have as well. This is using the virtual cell platform to accelerate machine learning in biology. So there are a lot of groups that are interested in virtual cells for like drug discovery and things like that. And it's a very interesting sort of approach to these things. And I don't exactly know what they mean by virtual cell platform, because we've talked about virtual cells in DevoWorm, but and they're very hard to sort of assemble. But this could be anything from biological modeling to actually modeling cells at the very detailed scale. So I don't really know kind of what the state of the art is. Perhaps we can talk about that in another meeting. Okay, so they also have the Indigenous and AI Machine Learning Workshop. They have, this is another invited talk. Are we having the wrong nightmares about AI? And this is Zeynep Tufekci. The abstract is, though seemingly opposite doom and optimism regarding generative AI's spectacular rise, will center on AGI, where even superintelligence is a pivotal moment. But generative AI operates in a distinct manner from human intelligence, and it's not a less intelligent human or on a chip slowly getting smarter anymore than cars or mere horseless carriages. It must be understood in its own terms. And even if Terminator isn't coming to kill us, or superintelligence isn't racing to save us, generative AI does bring a profound challenge, well beyond usual worries such as employment effects. Technology facilitates progress by transforming the difficult into easy, the rare into ubiquitous, the scarce into abundant, the manual into automated, and the artisan into mass-produced. While potentially positive long-term, these inversions are extremely destabilizing into easy, the rare into ubiquitous, the scarce into abundant, the manual into automated, and the artisan into mass-produced. While potentially positive, where are we here? I'm losing track. Okay. While potentially positive long-term, these inversions are extremely destabilizing during the transition, shattering the correlations and assumptions of our social order that relied on superseded difficulties as mechanisms of proof, filtering, sorting, and signaling. For example, while few would dispute the value of the printing press or books, their introduction led to such destructive upheaval that resulting religious wars caused proportionally more deaths than all of the other major wars and pandemics since combined. Historically, new technology's revolutionary impact comes from making what's already possible and desired cheap, easy, fast, and large scale, not from outdated or ill-fitting benchmarks that technologists tend to focus on. As such, artificial good enough intelligence can unleash chaos and destruction long before, if ever, AGI is reached. Existing AI is good enough to blur or pulverize our existing mechanisms of proof or accuracy, veracity, authenticity, sincerity, or even humanity. The tumult from such a transition will require extensive technological, regulatory, and societal effort to counter. But the first step is getting started having the right nightmares. So that's another invited talk. Looks like there's this Test of Time Award, which is, again, I guess an award that they give at the conference. And this award is the winner, Faster RCNN Towards Real-Time Object Detection with Region Proposal Networks. And this is Hao King Ren, Kai-Ming He, Ross Gershik, and Jian Sun. So this is a paper, state-of-the-art detection networks depend on region proposal algorithms to hypothesize object locations. Advances like SPPNet and fast RCNN have reduced the running time of these detection networks, exposing region proposal computation as a bottleneck. In this work, we introduce a region proposal network, or RPN, that shares full-time convolutional features with the detection network, thus enabling nearly cost-free region proposals. An RPM is a fully convolutional network that simultaneously predicts object bounds and objectiveness scores at each position. RPNs are trained end-to-end to generate high-quality region proposals, which are used by fast RCNN for detection. With a simple alternating optimization, RPN and fast RCNN can be trained to share convolutional features. With a very deep VGG16 model, our detection system has a frame rate of 5 frames per second, including all steps on a GPU, while achieving state-of-the-art object detection accuracy on Pascal VOC 2007 and 2012, using 300 proposals per image. And they have their code available on GitHub. So that is the award that they have for that. They have the Creative AI panel. They have some more oral sessions on generation and simulation. They have some position papers, optimization and algorithms sessions. On Friday, then they have the deep learning session, graph session, theory session, and then a poster session at 4:30 on Friday. And then they have, let's see, they have some other things going on Wednesday evening. And this is a social that I'm going to talk about in a minute. The role of AI in scientific peer review, that's kind of interesting. The Muslims in ML reception, the nonprofits working in openness and trust in AI, the Learning Theory Alliance, and Agent Safety Panel. Okay, then that's the end of the conference, Friday. So Friday is the end of the main conference. They have the closing session, poster session towards the end. So yeah, this is really interesting stuff. Definitely worth, if you can't attend, at least finding a way to think about these topics. Actually, there are two more things during the conference. There's a Signosky Hinton Award, and that is, I don't know who the speaker is here, but the abstract is: the brain processes information through many layers of neurons. The deep architecture is representationally powerful, but it complicates learning by making it hard to identify the responsible neurons when a mistake is made. In machine learning, the backpropagation algorithm assigns blame to a neuron by computing exactly how it contributed to an error. To do this, it multiplies error signals by matrices consisting of all the synaptic weights on the neuron's axons and farther downstream. This operation requires a precisely choreographed transport of synaptic weight information, which is thought to be impossible in the brain. Here we present a surprisingly simple algorithm for deep learning, which assigns blame by multiplying error signals by random synaptic weights. We show that a network can learn to extract useful information from signals sent through these random feedback connections. In essence, the network learns to learn. We demonstrate that this new mechanism performs as quickly and accurately as backpropagation on a variety of problems and describe the principles which underlie its function. Our demonstration provides a plausible basis for how a neuron can be adapted using error signals generated at distal locations in the brain, and thus dispels long-held assumptions about the algorithmic constraints of learning in neural circuits. So an interesting award talk there. And then finally, this last talk by Andrew Sachs, Demystifying Depth, Principles of Learning in Deep Neural Networks. So this is deep neural networks have revolutionized artificial intelligence, yet their inner workings remain poorly understood. This talk presents mathematical analysis of the nonlinear dynamics of learning in several soluble deep network models, offering theoretical insights into the role of depth. These models reveal how learning algorithms, data structure, initialization schemes, and architecture choices interact to produce hidden representations that afford complex generalization behaviors. A recurring theme across these analyses is a neural race. Competing pathways within a deep neural network vie to explain the data, with an implicit bias towards shared representations. These shared representations in turn shape the network's capacity for systematic generalization, multitasking, and transfer learning. I will show how such principles manifest across diverse architectures, including feed-forward, recurrent, and linear attention networks. Together, these results provide analytical foundations for understanding how environmental statistics, network architecture, and learning dynamics jointly structure the emergence of neural representations and behavior. So that was that. And then, so now we have the workshops. So the workshops, I'm going to switch to this tab, and I'm going to talk about some of the workshops, maybe some of the things that are interesting, some of the things that are notable, etc. This first one is Foundation Models for the Brain and Body Workshop. So this is talking about foundation models. This talks about foundation models and how foundation models are sort of can be used for this embodiment problem, basically. So our brains and bodies speak a rich and complex biological language of neural and physiological signals, a language that AI models are increasingly capable of deciphering as large-scale data sets become available. Recent advances in brain interfacing and wearable technologies, including EEG, intracortical electrophysiology, EMG, MEG, and ECG, have enabled a broad collection of these signals across real-world contexts and diverse populations. This growing wealth of data is driving a shift towards foundation models, which are large-scale pre-trained AI systems designed for learning from biosignals and generalize across diverse downstream applications for brain-computer interfacing to health monitoring. Realizing this potential, however, requires addressing the unique challenges that come with biosignal time series, which is that they are noisy, heterogeneous, and collected under variable conditions across subjects, devices, and environments. To meet these challenges, this workshop brings together neuroscientists, biomedical engineers, wearable tech researchers, and machine learning experts advancing foundation model approaches. Through interdisciplinary dialogue, we aim to catalyze the next generation of AI models that capture the complexity of brain, body, and behavior at scale. So this is, of course, something that we need if we want to do embodied cognition and kind of get different types of data streams and then integrate them in a way that is informative of what the body is doing as well as what the brain is doing in real time. This is a workshop on AI virtual cells and instruments. So again, as I said, there's this interest in virtual cells, especially in terms of drug discovery and development. So it says as the US FDA phases out animal testing requirements for drug discovery and development, AI tools have become widely adopted to simulate the effects of candidate drugs. We posit that building virtual cells and instruments with AI is poised to transform drug discovery and development by enabling large-scale simulation and interrogation of molecules, cells, and tissues. In our workshop, we will collaboratively define and promote this emerging scientific paradigm of AI to accelerate the drug discovery and development process in this new era. So, yeah, good luck with that. I'm not sure that this is, this is kind of like not necessarily what I was thinking when I was thinking of virtual cells, but this is GenPro CC, first workshop on generative and protective AI for content creation. This is I think about licensing, and I talk about this in my project management class, where you're thinking about licensing content and how generative AI models have kind of reached the typical intellectual property licensing agreements and how we need new open source licenses for generative AI tools. So the abstract here is recent advances in generative AI have empowered machines to create high quality content across diverse modalities, text, image, audio, and video, with impressive fluency and creativity. From GPT-4o and Stable Diffusion to Sora and MM Audio, the explosion of X-to-X generation, which is just any combination of like text to image or video to audio, is unlocking new frontiers in science, education, entertainment, and art. While Gen AI has shown significant potential in creative applications, these breakthroughs also raise pressing concerns related to safety, copyright, and ethical use. Generative models can be explored to spread misinformation, violate intellectual property rights, or diminish human agency in creative processes. As such, there is an increasing need to balance innovation with protection, ensuring that AI-powered creative tools are used responsibly and ethically. This workshop brings together researchers, creators, and practitioners at the intersection of content generation and IP protection. By uniting the generative AI and creator communities, the GenPro CC workshop aims to explore the latest advances challenges and opportunities in the rapidly evolving field. So again, this is, one of these things that kind of pops up when you have these new technologies that emerge and things that you need to sort of deal with as you go. This is embodied world models for decision making. This is, thinking about world models and embodiment. And here the abstract reads, world models infer and predict real-world dynamics by modeling the external environment, and they become a cornerstone of embodied artificial intelligence. They have powered recent progress in decision-making and planning for interacting agents. This workshop aims to bring together researchers working at the intersection of generative model, modeling, reinforcement learning, computer vision, and robotics to explore the next generation of embodied world models, or models that enable agents to understand, predict, and interact with the world through learned models. By focusing on embodiment decision making, this workshop seeks to advance world models beyond passive prediction towards active goal-driven interaction with the physical and virtual world. By emphasizing embodiment decision making, we aim to move beyond passive sequence prediction towards goal-directed interaction with the physical and simulated worlds. Okay. And then there's this AI for Matt. I think we talked about that last year, which is accelerated materials design. This is like chemical synthesis, material characterization, and using AI in that process. Okay, some things in combinatorial algorithms, some things on deep learning for code, imageomics, discovering biological knowledge from images using AI. That's kind of interesting. I didn't know they had the term imageomics for it, but that's a new one to me. Op 2025 optimization for machine learning. Let's see. This is Lock Large Language Models Workshop. Prevent unauthorized knowledge use from large language models. Deep dive into undistillate, unfine-tunable, uncompressible, uneditable, and unusable. So this kind of sounds interesting. This is kind of, I guess, a cornucopia of things. Large language models have emerged as a transformative tool across research and industry, revolutionizing how we interact with information. However, their immense capabilities bring critical security challenges. The same features that drive innovation can be exploited for malicious purposes through unauthorized distillation, fine-tuning, compression, or editing. These vulnerabilities pose severe threats, including intellectual property theft, the generation of sophisticated disinformation, the bypass of safety alignments, and the erosion of user trust in AI systems. This workshop aims to bring together researchers and practitioners from academia and industry who are advancing the frontiers of large language model security and protection. We seek to confront the unauthorized use of large language models head-on by exploring novel and robust mechanisms designed to make these models inherently resistant to exploitation while maintaining their beneficial capabilities. The workshop also hosts the 2025 Trust AI Rising Star Award. So this is kind of what they mean by all these things. There's the undistillable large language model, which is preventing unauthorized model replication and intellectual property theft. Unfine-tunable large language models, resisting malicious parameter updates and behavior alterations. Uncompressible large language models, which is maintaining model integrity against unauthorized compression. There's uneditable large language models, safeguarding against knowledge tampering and misinformation injection. And then unusable large language models, ensuring traceability and preventing misuse through watermarking and verification. There's some practice-oriented things there. Algorithmic collective action, which looks kind of interesting, which is looking at collective action in economics and sociology and thinking about how to understand like algorithms that enable collective action, whether good or bad. This is UniReps, unifying representations and neural models. When, how, and why do different neural models learn the same representations? And this, of course, connects to neuroscience and how brains do the same thing in terms of representations. This is CauseScience, uncovering causality in science. Okay, so this is causality in science. They're abstract. Many scientific questions inherently possess a causal dimension, from estimating treatment effects in personalized healthcare, understanding biological mechanisms, to evaluating the social and environmental impacts of governmental policies. At the same time, the recent surge in causal learning has unlocked the potential to extract reliable cause and effect relationships with complex high-dimensional data. Despite promising breakthroughs in causal reasoning and discovery, translating those methods into day-to-day scientific practice remains challenging, as it requires transitioning from controlled or simplified demonstrations to robust application-driven research and problems. This workshop is designed to bridge the translational gap by fostering collaboration across the broad spectrum of disciplines, including ecologists, biologists, and social scientists, with a shared interest in both the theoretical and practical aspects of causal inference. And so they have 3 questions that they focus on here. Where does causality manifest across different applied science domains? When can causal learning techniques effectively accelerate scientific discovery? And how can we best integrate causality with domain expertise in real-world scientific data? And so by promoting a bottom-up research paradigm that starts with concrete real-world problems, we aim to do a couple of things. The first is surface unresolved challenges that the theory must address. The second is releasing causal benchmark tests that reflect real scientific constraints. And then third, seed collaborations between domain experts and machine learning researchers that outlive the event. So they want to understand in this workshop the dual roles of causality, both as a tool for reasoning and interpretation, and as a mechanism for planning and experimental design. And so that's kind of where they want to go with that. A lot of speakers here, organizers. So yeah, this is interesting work. Causality is definitely, kind of a necessary component of intelligence and learning, but kind of understanding how you can represent that in a model is a different story altogether. It's very hard to get to. Okay, so let's see. There's this one, Dynamics at the Frontiers of Optimization, Sampling in Games. This one is, again, we'll go to the workshop website. This is dynamical systems have played an important role in the analysis and design of algorithms. Ideas ranging from variational methods, differential and symplectic geometry, numerical analysis, and control theory have paved the way for establishing non-asymptotic convergence guarantees in optimization and sampling as equilibrium computation in games. Yet, the distinct mathematical backbone of these tools often creates barriers of entry, for researchers and practitioners in machine learning. This workshop aims to lower that barrier by highlighting the unified role of dynamical systems across these domains. We will convene optimization, sampling, and game theory experts to foster cross-disciplinary dialogue and collaboration. Emphasis will be placed on emerging applications in machine learning, such as diffusion models, distributed and adversarial training, agentic AI, where dynamical systems perspectives are increasingly central. Through a combination of talks, posters, and open discussions, we hope to catalyze new collaborations and broaden the accessibility of these foundational methods. So this is, again, kind of bringing dynamical systems into the mix. Mathematical foundations and operation integration in machine learning. That's MLXOR. The second workshop for Gen AI in health. AI for non-human animal communication, which looks interesting. Let's see what that looks like. The past few years have seen an unprecedented surge in both the availability of bioacoustic data and the sophistication of AI/machine learning models. This convergence presents a unique window of opportunity to revolutionize our understanding of animal communication and biodiversity. However, achieving this requires a conscious effort to integrate the disciplines of AI/machine learning and ethology. This workshop will explore the intersection of artificial intelligence and bioacoustics, aiming to address challenges in processing complex bioacoustic data and interpreting animal signals in order to advance our understanding of non-human animal communication. Join us for a poster session, keynote talks, and a panel discussion as we explore key opportunities to use AI to decipher animal languages and thus deepen our understanding of the natural world. So a nice workshop there. Here's the first workshop on efficient reasoning. This is, of course, reasoning in large language models. Recent progress in large reasoning models, or LRMs, like OpenAI O1 and DeepSeek R1, have been pivotal for tackling complex applications from mathematical and code reasoning to advanced symbolic and agentic planning. Their success often relies on test time scaling, which involves increasing the generation length or depth. However, these approaches incur significant efficiency bottlenecks during training and inference. To overcome these limitations, further advancements are needed in data, algorithms, and systems applicable across various domains, as exemplified by work such as S1, Z1, and Virl. The proposed workshop will bring together researchers and practitioners to rethink efficient reasoning under tight compute, memory, latency, throughput, and cost budgets, with the goal of translating theoretical breakthroughs into practical, deployable solutions. Then there's this workshop, Math AI, the fifth workshop on mathematical reasoning in AI. Of course, this is on mathematical reasoning. And we go to the workshop website, and this is the overview. Mathematical reasoning is a fundamental aspect of human cognition that has been studied by scholars ranging from philosophers to cognitive scientists and neuroscientists. Mathematical reasoning involves analyzing complex information, identifying patterns and relationships, and drawing logical conclusions from evidence. It is central to many applications in science, engineering, finance, and everyday contexts. Recent advancements in large language models have unlocked new opportunities at the intersection of artificial intelligence and mathematical reasoning, ranging from new methods that solve complex problems or prove theorems to new forms of human-machine collaboration in mathematics and beyond. This workshop is centered on the intersection of deep learning and mathematical reasoning, with an emphasis on, but not limited to, large language models. Our guiding theme is, to what extent can machine learning models comprehend mathematics? What applications could arise from the capability? To address this question, we aim to bring together diverse participants from different backgrounds, institutions, and disciplines. And they're going to focus on sort of the following areas: humans versus machines, how we can have a comparative study of human-level mathematical reasoning and current AI techniques. How do they differ, complement one another, or intersect? Measuring mathematical reasoning. How do we design benchmarks which accurately evaluate mathematical reasoning abilities, especially in an era of large language models? New capabilities. How do we move beyond our current techniques? Education. What roles can deep learning models play in mathematics education, especially in contexts with limited educational resources? And then finally, applications. What applications could AI systems enable in the near and long term? Example domains include software verification, sciences, engineering, finance, education, and mathematics itself. So yeah, that's that one. We have practices in video generation and evaluation. What makes a good video? in workshop on multi-turn interactions in large language models, recent advances in time series foundation models, machine learning in the physical sciences. This is ML4PS, which happens every year. Regulatable ML towards bridging the gaps between machine learning research and regulations. CogInterp, interpreting cognition in deep learning models. Let's see, new perspectives in graph machine learning. And of course, in graph machine learning, we have all sorts of connections with network theory and complex network theory and graph theory. Let's see, program, this has a number of talks. This has an entire agenda here. So, keynote here, Yusu Wang, learning generalizable algorithm procedures via graph neural networks. This oral presentation beyond sparse benchmarks, evaluating graph neural networks with realistic missing features. Then there's this other oral presentation, Gromov-Wasserstein graph coarsening. Another oral presentation, robust tangent, space estimation via Laplacian eigenvector gradient orthogonalization. This talk by Rohira Leskovac, relational foundation models and end-of-task specific graph neural networks. Another oral presentation, causal structure learning in Hawk's processes with complex latent co-founder networks. Another oral presentation on graphs and tables, zero-shot node classification with tabular foundation models. There's this talk by Nina Miolani, topological deep learning. Matthias Niepert, learning approximately equivariant GNNs for simulations of physical systems. Another one here, teaching large language models to reason on graphs with reinforcement learning. And yeah, so those are the talks. And then they have these other areas that they were interested in, which would be, things like symmetry and equivariance and group theoretic graph models, different types of geometric models, graph diffusion models and graph generative models, continuous limited and infinite width analysis of graph machine learning, graphs for science and graph-based simulations, causality and directed acyclic graph learning, self-supervised and semi-supervised graph machine learning, and quantum graph machine learning. So those are kind of hot topics in the area that they also are interested in. So I don't know if Vidhi had something. Graph machine learning is part of what I presented last week. Okay, good. So that's good. Yeah, we do that, of course, in DevoWorm, and it's an area that I think is a nice fit to some of the things we're doing with networks. Did you have any comments or other comments on
No, it's just interesting how they have like multiple needs or like different like timing slots, and then they're doing different things. It's interesting to know something like that. Yeah, and whatever is going on.
Yeah. Okay, so let's see. Let's go back to the workshops. There are a lot of workshops. We're getting towards the end, I think. Let's see. There's this learning to sense, which is exploring the joint optimization of sensors and machine learning models, pushing beyond traditional paradigms of data acquisition and processing. We aim to rethink the foundations of how machines can sense the world by replacing handcrafted ISPs, leveraging learnable sensor layouts, and adopting task-driven. Okay, and let's see. So they welcome original contributions and position papers on the following topics: sensor optimization for, say, like computer vision, raw to task and raw to label approaches for visual tasks, co-design of neural networks and sensor hardware, low bit energy efficient sensing for embedded or mobile devices, benchmark data sets and metrics for evaluating sensor model pipelines, generalization and robustness of sensor model systems in real world conditions, and then failure case studies and negative results in joint optimization pipelines. Okay, so that's learning to sense. And then there's this what can't transformers do? And so this is the abstract here. With most advances in large foundation models being empirical, our theoretical understanding of what transformers can compute, express, and learn still lags behind. This workshop will convene theorists and empiricists to chart a rigorous agenda for the next generation of LFMs, asking what can and can't transformers do. So this is, again, we talked about moving beyond transformers or post-transformer architectures. So this is actually kind of an interesting thing to think about, because we have to know what they can't do in order to think about the post-transformer landscape. They welcome both formal analysis and empirically grounded studies that shed light on theoretical questions, aiming to close the gap between proofs and practice while fostering new interdisciplinary collaborations. And if you go to the workshop website, this is, of course, the sort of the call for papers. So the core themes are theoretical analysis of transformer capabilities, including expressivity, learnability, inference timescaling, in-context learning, and the effects of architectural components. There's also empirical studies of transformer behavior that inform theoretical understanding, including architectural or training innovations, mechanistic studies of failures, and comparisons of theorized and observed capabilities. So the accepted papers here, there are a number of different spotlights and posters. There's encoder-only next token prediction. There's on the role of transformer feed-forward layers and nonlinear inline context learning, or in-context learning. Why do transformers fail to forecast time series in context? So there's some work on in-context learning and time series and nonlinearity. Then there are the posters, which again focus on in-context learning. Some things about circuit complexity limits, some things about delayed attention training in terms of how that affects performance. Let's see. In-context learning and diffusion language models. In-context learning is implicit optimization. In-context learning is not gradient descent unless you initialize your transformer right. Out-of-distribution generalization of in-context learning, a low-dimensional subspace perspective. Towards the understanding multimodal in-context learning. Transformers in the dark, navigating unknown search spaces via noisy feedback. And when transformers can or can't generalize compositionally, a data distribution perspective. So those are all kind of thinking about these types of limitations of transformers and the transformer architecture. Okay. Then we have learning from time series for health, which is applying time series data to health contexts and using machine learning to understand that. Data on the brain and mind. Non-Euclidean foundation models and geometric learning, advancing AI beyond Euclidean frameworks. And, this again is thinking about non-Euclidean learning. So non-Euclidean learning is quickly gaining traction in the field. Non-Euclidean spaces such as hyperbolic, spherical, and mixed curvature spaces have been shown to provide more efficient and effective representations for data with intrinsic geometric properties like hierarchy, symmetry, and heterogeneity. Integrating foundation models in non-Euclidean spaces has great potential to enhance their ability to capture and model the underlying structures in relationships and conflict through real data, leading to better performance, generalization, and interpretability. This workshop focuses on the intersection of non-Euclidean representation learning and foundation models, exploring its potential benefits, challenges, and future directions. Okay, then there's evaluating the evolving large language model lifecycle, workshop on mechanistic interpretability, frontiers in probabilistic inference, AI for science, the reach and limits of AI for scientific discovery. This is symmetry and geometry neural representations, which they've done for a number of years. Just kind of working on this area of topological learning and geometric learning. And so, yeah, there are a lot of workshops here. Another workshop on space and vision, language, and embodied AI. There's a whole workshop on IIT Delhi. So I guess that's just kind of what they're doing. There's the Computational Neurosociety workshop. And yeah, so that's it. And then in Mexico City, there are a few other workshops, which we won't talk about right now. But that all looks very interesting. That's a huge brain dump of workshops, I know. But, this is, again, important to understand what the shape of the field is looking like going forward and kind of thinking about, how our work might interface with that. So this is the thing I was talking about. This is going to happen in San Diego. This is the AI for Science panel and happy hour. The only reason I mention this is because it's kind of interesting that, there's this sort of social component where, people are thinking about using AI in science, whether you're developing foundation models for biology, working on materials discovery, or thinking about how AI can accelerate research. This is a great opportunity to hear from experts pushing the boundaries and to meet others doing the same. So that's something that's happening. Okay, so the next thing I want to talk about is this. So that's NeurIPS 2025. That's coming up in the next week and a half. And so, this happens every year in December. So just keep thinking about this, and maybe we'll talk about it next week. Now, this is a paper I wanted to talk about. This is an arXiv paper. This is on Alpha arXiv. So this is a tool where you can render arXiv papers, and you can actually chat about arXiv papers, but I don't have the chat function open. So this is just kind of the arXiv paper called Evolution Strategies at the Hyperscale. This is a group from Mila in Quebec, NVIDIA, and the University of Oxford. So this is from the arXiv last week. And so again, I talked about how the Google tool AlphaEvolve, how that, the methods are kind of opaque, and I was interested in how people are using evolutionary computation in machine learning with large language models and so forth. So this kind of gives maybe another kind of view on this using an approach called evolution strategies. So this is the abstract. We introduced evolution-guided general optimization via low-rank learning, which they use the acronym EGROL. An evolution strategies algorithm designed to scale backprop-free optimization to large population sizes for modern large language network architecture, large neural network architectures with billions of parameters. ES is a set of powerful black box optimization methods that can handle non-differentiable or noisy objectives with excellent scaling potential through parallelization. Naive evolution strategies becomes prohibitively expensive at scale due to the computational and memory costs associated with generating matrix perturbations and the batch matrix multiplications needed to compute per member forward passes. Eggroll overcomes these bottlenecks by generating random matrices to form a low-rank matrix perturbation that are used in place of the full-rank perturbation E. As the overall update is an average across the population of n workers, this still results in a high-rank update with significant memory and computational savings, reducing the auxiliary storage per layer and the cost of a forward pass from OMN to ORM plus N when compared to full-rank evolution strategies. Eggroll's efficiency results in a 100-fold increase in training throughput for billion parameter models at large population sizes, nearly reaching the throughput of pure batch inference. Theoretical analysis reveals our low-rank update converges with the full-rank update at a fast 1 over R rate. Our experiments show that Eggroll does not compromise the performance of evolution strategies in tabula rasa reinforcement learning settings, despite being faster. It is competitive with GRPO as a technique for improving large language model reasoning. And then Eggroll enables stable pre-training of nonlinear recurrent language models that operate purely in integer data types. So they have their code on GitHub. And this is a schematic visualization of the platform. So they have the initial rates, they have rank 1 perturbations, then they have a fitness evaluation. That gives you a weighted average, and this gives you the final rank and update. So they use a fitness evaluation here. That is essentially where they perturb the matrix and then of initial weights, and then they give a fitness evaluation by evaluating sort of the variety of each perturbation. And so this is the fitness evaluation with the fitness function, which then yields a weighted average and then gives you this update. So evolution strategies as an approach is an old, it goes back to the 1970s. So they mentioned, they don't really talk about like the background too much, but they say it's an attractive alternative to first order methods based on gradient backpropagation for several reasons. So first, evolution strategies does not require differentiability, so it can optimize a broader class of models, like models of discrete parameterization spaces, these are cellular automata, and can optimize objectives when gradients are unavailable or noisy, like outcome-only rewards in large language model fine-tuning. Second is that evolution strategies is more robust to noisy and ill-conditioned optimization landscapes of things that aren't convex. Unlike gradients, population-based exploration smooths irregularities, tolerates discontinuities, and mitigates issues like ill-conditioned curvature or vanishing and exploding gradients in long-range or recurrent settings. Third, evolution strategies is highly amenable to scaling through parallelization, since fitness evaluations are independent across population members and require only the communication of scalar fitnesses, which map cleanly onto modern inference infrastructures and yields nonlinear speedups on large clusters. By contrast, backpropagation requires communicating and aggregating gradients across devices, yielding updates with high memory and computation costs. Additionally, backpropagation requires special care when training models with low precision data types, whereas ES can directly optimize any model with the same data types used at inference time. Together, these properties position evolution strategies as a potentially powerful foundation for training large, discrete, or hybrid architectures and an end-to-end system with non-differentiable components, including large language models. So there are a lot of problems with deploying evolution strategies at scale. So in deep learning architectures, for example, The majority of trainable parameters form linear mappings represented by matrices. Naively adapting evolution strategies therefore requires generating full-rank matrix perturbations that replicate the entire parameter set for every population member. This inflates memory cost and forces frequent movement of large weight tensors. Evaluating these perturbations then requires a separate sequence of matrix multiplications per member, so the total compute and wall clock time scale roughly with the population size and sequence length. In billion parameter regimes, that's pretty untenable. To mitigate both memory and computational bottlenecks, we introduce evolution-guided general optimization via low-rank learning, or EGRL. This is an ES algorithm that allows for efficient training of neural network architectures. This is analogous to LoRa in their low-rank adapters and gradient-based training. EGRL generates low-rank parameter space perturbations for evolution strategies. So instead of sampling a full-rank member, we sample different components and form this matrix. This reduces auxiliary perturbation matrix storage from Mn to Mn, M plus Nr per layer, and proportionally reduces tensor movement. So they kind of decrease the memory requirements for this. So they kind of go through some of their methods, and this is the evolution strategies methodology. So this is what I wanted to see in the other paper. So evolution strategies, as they define it here, is a set of black box methods for optimizing general systems. ES has emerged as a useful alternative to gradient-based methods, particularly when a system is noisy or non-differentiable. Our problem setting focuses on fitness functions whose parameters are matrices. Our goal is to find matrix M star that maximizes the fitness function M star. In comparison to gradient-based methods, which use derivatives of the function Fm to update the parameters M directly, evolutionary methods update a population distribution over the parameter space. This is achieved by learning a set of parameters theta to maximize the expected fitness Fz under a population distribution pi m given theta. And then this is there. I guess it's a Jacobian. Taking derivatives of j theta yields the gradient here, which is used to update the population's distribution parameters using stochastic gradient descent with a suitable step size alpha t. The log gradient is known as the score function, which avoids taking gradients directly through the fitness function in equation 1. Okay, so this is the Wikipedia page on evolution strategies. This is just the best sort of summary I could come up with. It goes back all the way to 1973, so this has a very deep history. Evolution strategy is a subclass of evolutionary algorithms, which serves as an optimization technique. It uses the major genetic operators mutation, recombination, and selection of parents. So every evolutionary algorithm consists of a program, an encoding, and they're a population of encodings. So you have those encodings that are replicated at a certain population size. The reason, of course, you need a population is because evolution works on populations. Each encoding then can be mutated, can be recombined, and then those individuals are evaluated by a fitness function. Those programs can also replicate and maybe sometimes reproduce in ways that involve crossover, so you get maybe like a sexual reproduction, and you end up with this system that operates kind of like a biological population subject to selection, and then that's supposed to yield you the best strategies. So your population of encodings might represent a bunch of potential solutions to a problem, and you recombine and mutate those encodings, and you can end up with the most optimal solution, or maybe very interesting solutions that you never would have come up with before. Years ago, they had a lot of different applications on the web where you could do things like breeding pictures using evolutionary algorithms, where you'd have a bunch of like pieces of abstract art that you could evolve by generating a bunch of potential pieces of art and then select using the selection operator, sort of, maybe as based on the person who's selecting it, what they like, their aesthetic preferences. So you just simply select different images and promote them, and then those would reproduce, and you'd get variations on that, and then you'd pick the best one there, and those would reproduce, and you'd end up getting these populations that gave you variation. You could select on that variation, and you'd end up with sort of the optimal image based on your aesthetic preferences. A fun exercise in showing how an evolutionary algorithm works. So evolution strategies is a subset of that, or a subset of evolutionary computation, but it has certain properties that are different from the evolutionary algorithm. So this article here, it talks about how these optimization techniques were actually created in the early 60s, but then really kind of were developed formally in the early 70s. So in 73, we had evolutionary strategies introduced with mutation and selection. You had these meta-evolutionary strategies in 2007, weighted multi-recombination evolution strategies in 2006, natural evolution strategies using an evolutionary gradient. So, these are kind of predating a lot of the machine learning techniques, the way they're built today. And so, there are a lot of ways you can use evolution strategies for pure optimization problems. So, in this case, the gradient is a fitness landscape where you follow that fitness landscape to the highest levels of fitness instead of following it downward to the lowest error. So there are a lot of different ways evolution strategies works. So some notes about the methods here. Evolution strategies use natural problem-dependent representations, so problem space and search space are identical. In common with evolutionary algorithms, the operators are applied in a loop, so you generate variation, you select upon that variation, or variation is generated, and you're improving the solution as you do that. You're moving up to a peak in that fitness landscape. An iteration of the loop is called a generation. The sequence of generations is continued until a termination criterion is met. A special feature of evolution strategies is the self-adaptation of the mutation step sizes and the coevolution associated with it. So the ES is briefly presented in the standard form. The row-valued chromosome contains, in addition to indecision variables N prime, and mutation step sizes, where the value of often one mutation step size is used for all decision variables, where each has its own step size. Mate selection to produce offspring is random. First new mutation step sizes are generated per mating by intermediate recombination of parental mutation step size with subsequent mutations. And then they give some math here. This results in an evolutionary search on two levels. First at the problem level itself, and second at the mutation step size level. In this way, it can be ensured that evolution strategies searches for its target in even finer steps. However, there's also the danger of being able to skip larger invalid areas in the search space, only with difficulty. So you have this work out this procedure of sort of evolving your population, and in doing so targeting a certain part of the search space, and then these strategies are sort of optimized for that search space, and you end up with sort of the best solution to finding the optimal points on that search space. So that's what I mean by strategies. So the evolution strategies knows two variants of best selection for the generation of the next parent population. So mu is the number of parents, and then there's the number of offspring. So that's where we have mu and the number of offspring. The mu best offspring are used for the next generation, and so mu is usually the number of offspring divided by 2. And then mu plus offspring, the best are selected for a union of euparents and the number of offspring. And so this, of course, there are different ways that you can implement this. Bach and Schwaffel recommend the value for the number of offspring should be approximately 7 times the mu, which is the number of parents, whereby mu must not be chosen too small because of the strong selection pressure. So you need to have a large initial population of parents, and then a 7-fold number of offspring, basically tuning up that replication parameter to produce more variation. Suitable values for mu are application dependent and must be determined experimentally. The selection in the next generation evolution strategies is deterministic and only based on the fitness rankings, not on the actual fitness values. The resulting algorithm is therefore invariant with respect to monotonic transformations of the objective function. The simplest and oldest evolution strategy, 1 plus 1, operates on the population size of 2. The current point parent and the result of its mutation. Only if the mutant's fitness is at least as good as the parent one, it becomes the parent of the next generation. Otherwise, the mutant is disregarded. More generally, the number of offspring mutants can be generated and compete with the parent. So there's 1 plus the number of offspring and 1, and then number of offspring. In that case, the best mutant becomes the parent of the next generation, while the current parent is always disregarded. For some of these variants, proofs of linear convergence in a stochastic sense have been derived on unimodal objective functions. Individual step sizes for each coordinate or correlations between coordinates are essentially defined by an underlying covariance matrix, are controlled in practice either by self-adaptation or by covariance matrix adaptation. When the mutational step is drawn from a multivariate normal distribution using an evolved covariance matrix, it has been hypothesized that this adapted matrix approximates the inverse Hessian of the search landscape. This hypothesis has been proven for a static model relying on a quadratic approximation. In 2025, Chen et al. Proposed a multi-agent evolution strategy for consensus-based distributed optimization, or a novel step adaptation method is designed to help multiple agents control the step size cooperatively. So there are a lot of innovations in this area and a lot of ways to apply these algorithms, but the basic goal of the approach remains similar. And so again, there are different ways that you can use evolution strategies. Of course, we also have other forms of evolutionary computation. We have different forms of simulating evolutionary processes and so forth. So now I wanted to talk about this interview with Ilya Sutskever. Remember, we talked about scaling and sort of the problems maybe we're running up against with scaling, how we're making models bigger but not necessarily better. They have some of the same problems that the smaller models have. And so at this point, we're reaching a place where maybe we need to rethink how we're building the smaller models before we scale them up. And so this is an interview. This is from Tim Kellogg's Blue Sky account, and he has a couple of threads on this. This was from a few days ago. So this is November 25th. And so this is a quote here. It's back to the age of research again, just with big computers. And so the idea is that we need to rethink our algorithms that we're scaling up. So instead of thinking of scaling as sort of the holy grail of intelligence or superintelligence or what have you, we need to go back to the drawing board in a number of ways. So it's this quote here: "These models somehow just generalize dramatically worse than people. It's a very fundamental thing. So our small models are generalizing worse than people. When we scale them up in terms of size, they're generalizing worse than people as well. And that's kind of the idea. So in other words, we've hit this is, Gary Marcus would say we've hit a wall of some type. So And so Tim Kellogg says, this is the theme. You can't have AGI without existing in and learning from the real world, which of course is true in terms of training, but also in terms of embedded systems, in terms of continual learning and things like that. This is Dwarkesh Patel. The thing that happened with AGI and pre-training is that in some sense they overshoot the target. You will realize that a human being is not an AGI because a human lacks a large amount of knowledge. Instead, we rely on continual learning. If I produce a super intelligent 15-year-old, they don't know very much at all. A great student, very eager, you can say. You go and be a programmer, you go and be a doctor, go and learn. So you could imagine that the deployment itself will involve some kind of learning, trial and error period. It's a process as opposed to you drop the finished thing. So this is kind of drawing at this distinction between training a model with information, with data, and then it having some experience with the data. So, the idea is that you have like a 15-year-old or a teenager whose brain is not fully developed and also has not had a lot of experience in the world, can have a lot of information, but they will not be as successful without that sort of, first of all, there's some biological development that still needs to happen, some maturity, but then also the experiential part, which needs to be in place. And how much experience do you need to be a great X or a great Y? Well, that's the problem that they're trying to figure out. So you can dump a bunch of training data into this model, but it doesn't necessarily translate into super intelligence, is the point. And so Tim Kellogg says, Dwarkesh nervously, kind of this quote, ah ha ha, yes, of course, the value function for human emotions makes perfect sense. Then he says, again, another Dwarkesh Patel quote, emotions are so simple, it would be cool to map them out in a human understandable way. And then pauses an extremely awkward amount of time. And then this is another quote from the interview. Does hunger count as an emotion? It's debatable. But I think, for example, our intuitive feeling, and that's kind of the caption in the clip here. He must be doing it on purpose, just handing out quotable quotes on repeat for an hour and a half. This is just kind of, busting his chops, as they say, because it's kind of like he's backtracking in a lot of ways as to what was promised in the past few years. So this is, let's stop picking on Ilya. Scaling consumed so much economic attention that it was difficult to convince your boss or a VC to let you look anywhere else. And that can't have good consequences. That surely leads to blind spots. That's basically the takeaway from this whole thing. So yeah, I just wanted to go over that and talk about that sort of outcome. Definitely there's a lot of rethinking of what people have been ceaselessly hyping for the last few years. And it's interesting to think about that in the larger context of modeling and of, some of the things that I think a lot of people had already identified, which is that, we have a lot more hype than sort of informative outcomes. So this is just kind of an opinion on that. Okay, so I think I'll finish up with this article. This is a review. This is something that we've talked about. We've talked a lot about metaphors in our group, and we've talked about computational psychiatry. And so this is kind of the intersection of those two areas. So this is an expert review on the history of metaphorical brain talk in psychiatry, the Molecular Psychiatry Journal, and kind of in the history of the field of psychiatry, how they've used metaphors of the brain and how that's kind of played a role in the formation of the field and the evolution of the field. So from the abstract, from the very beginnings of our field in the late 18th century, psychiatrists have engaged, often extensively, in metaphoric brain talk, rephrasing descriptions of mental processes and unconfirmed brain metaphors, such as diseased working of or the brain convolutions, which is kind of a description of some sort of mental illness. In the late 19th century, Kraepelin criticized the later developments of such approaches, termed brain mythology by the philosopher psychiatrist Jaspers in 1913. In this essay, I will review the history, meaning, and significance of this phenomena and reach 4 conclusions. So the first is that this trend continued to the present day in metaphors such as the broken brain and the use of simplistic and empirically poorly supported explanations of psychiatric illness, such as depression being due to an imbalance of serotonin in the brain. So things like broken brain, imbalance, those sorts of things are all indicative of illnesses or of dysfunctions. Second, our language stems from the tension in our profession that seeks to be part of medicine, yet declares our main focus is treatment of the mental. We feel more comfortable with the reductionist approach to brain metaphors, which, even though at times are self-deceptive, nevertheless reinforce our commitment to and membership in a brain-based medical specialty. Third, metaphorical talk can also be seen as a promissory note of our profession, a pledge that the day will come when we can indeed explain accurately to ourselves and to our patients the brain basis of the psychiatric disorders from which they suffer. So basically, kind of guaranteeing that there's maybe a cure on the horizon. And that's irrespective of whether that's actually true, but speaking in those terms. Finally, moving away from metaphorical brain talk would reflect the increasing maturity of both the research and clinical aspects of our profession. So this is just arguing against a lot of these metaphors, which are maybe counterproductive. So he focuses on this idea of metaphorical brain talk, which he defines as describing the disturbed mental processes and psychiatric illnesses in terms of brain function in ways that appear to be explanatory, but actually have little to no explanatory power. So you can see this across the history of the field, going way back to at least in this case, to the 19th century, thinking about asylum psychiatry, thinking about the biological psychiatry revolution of the late 1800s, early 1900s, and then kind of thinking about brain mythology, and then thinking about how we talk about psychiatry today in terms of brain metaphors. So a lot of really interesting historical material here, a lot of interesting things going on in the history of the field, and a lot of lessons for the modern day. And so, a lot of early metaphors involve maybe our limited understanding of the brain. And so Maynard, who is one of the people from that era, the late 1800s, early 1900s, used to construct brain pathways just kind of through metaphor. So thinking about different ways in which things worked in the brain when we didn't know a lot about the brain. Paradigmatic for the spirit of the time is the highly speculative fusion of psychopathological findings with anatomical findings and pathogenetic claims, which in Maynard, following an old tradition, related in particular to vascular-dependent differences in brain nutrition. Maynard's own student Auguste Forel called his brain pathways fantastical constructions. We conclude with one of further critique from Phelps. What about Maynard's work made it cogent and compelling? What about it seemed capable of dispelling the mystery of the nervous system and dispensing with the unique inwardness of the mind? Part of the answer lies with Maynard's images of the brain's material and co-location of its fleshy, fibrous inner stuff with the interiority of the mind. By delineating various fiber systems in the brain and nerves, then deducing their different functions on the basis of their winding pathways, Maynard elaborated new shapes and textures inside the brain, and by doing so, he elaborated and fleshed out functions of the mind. But even as he imagined these fibers as pathways or tracts inside the brain, he co-extended them and co-located them as pathways somehow equally inside the mind. So again, thinking about brain anatomy, not necessarily connecting that with the function. And so you just kind of make up the story about what's going on in the brain. and how it's working, but it's totally disconnected from reality or from some good functional model. His success, Phelps suggests, was due to his ability to connect what he saw inside the brain with an image of what he described as inside the mind by his combination of material and metaphorical techniques. Instead of analyzing the facts in an unbiased way and using the great extension of our experience and mental efforts to get square with things, they pass at once to a one-sided consideration of the extra psychological components of the situation, abandon the ground of controllable observation, translate what they see into a jargon of wholly uncontrollable brain mythology, all of that with the conviction that this is the only admissible and scientific way. So it's pretty, well, sounds like we're describing a scam artist, but we're not. It's just someone who's making up a story and putting that out in front of the data, which, again, is a lot of times how things work when you're trying to interpret data. But I mean, sometimes, and it's not bad necessarily if you need a mental model. You need to map everything to a mental model. But of course, it's also, you can get carried away, I guess, is maybe one of the ways to do this. And then, you're using metaphors too loosely. This is always the problem with metaphors. You use a metaphor, and it's always imperfect because you're mapping one thing to another. But sometimes the metaphor takes over. Next, we examine a text on a similar theme from a quite different source, the psychiatrist-philosopher Karl Jaspers. In the introduction to his first edition of General Psychopathology, which was in 1913, he writes, "The still widespread somatic prejudice is everything mental cannot be examined as such, it is merely subjective. If it is to be discussed scientifically, it must be presented anatomically, physically, as a physical function. For this, it is better to have a preliminary anatomical construction, which is considered heuristic, rather than a direct psychological investigation. Such anatomical constructions are quite fantastic, which is in reference to Maynard, and are rightly called brain mythologies. Things that have no connection to one another, such as cortical cells and memory images, brain fibers, and psychological associations, are brought together. There is also no basis for these mythologies insofar as not a single specific brain process is known that could be assigned to a specific mental process as a direct parallel phenomenon. So we might think that recent scientific developments over the rest of the 20th century eliminated the need for metaphorical brain talk. Right? As you know more about the brain, you have better models, you have more constrained metaphors because you have the data, you have the mechanism, and you don't need to use them as sort of a way to link things. But we provide 3 examples here suggesting that this is not the case. So just because we know more doesn't mean we stop using metaphors improperly. First, in a series of articles published over several decades, the distinguished psychologist Paul Meehl proposed that a cognitively and psychometrically sophisticated genetic single locus model for schizophrenia spectrum disorders. A core part of this theory was equating cognitive and neurobiological parts of his theory, as expressed here in 1962. The cognitive slippage is here conceived as a direct molar consequence of synaptic slippage, potentiated by the disruptive effects of aversive control and inadequate development of interpersonal communication sets. So this phrase synaptic slippage is, of course, kind of an incomplete sort of account of what's going on in the brain. So it's just kind of this metaphor that keeps replicating itself in the literature, and it sounds nice, but it's inaccurate. Second, in 1985, a leading biological psychiatrist, Nancy Andreessen, published a widely cited book whose title was A Paradigmatic Example of Metaphorical Brain Talk, which is The Broken Brain. She writes, for example, that recent advances in research have taught us that many forms of mental illness are due to abnormalities in brain structure or chemistry. Psychiatry is moving from the study of the troubled mind to the broken brain. So this is, again, these troubled and broken words are kind of giving us this image or this framework of dysfunction. In a later section, she describes using broad metaphors the kind of brain abnormalities that occur in psychiatric disorders. The various forms of mental illness due to many different types of brain abnormalities. Sometimes the fault may be in the pattern of the wiring or circuitry, sometimes in command centers, and sometimes in the way messages move along the wires. So again, wires, command centers, pattern of wiring or circuitry, and they're just kind of viewed as like they're, when you have a mental illness, those things are off balance. And of course, all of those are metaphors. Command center being a very good example, or messages moving along the wires is another good example. And so, it's kind of hard to, it's easy to kind of imagine what the abnormality is, but then it's harder to map that back to the science. And so a lot of times, again, you get these metaphors that get ahead of what's actually going on. Third, in an important development of the history of neuroscience in the early 1960s, cell bodies and neuronal pathways in the putative monoamine neurotransmitter dopamine, norepinephrine, and serotonin were demonstrated in mammalian brains. Within a few years, prominent psychiatric researchers proposed that abnormalities of function in these neurotransmitters were the major cause of three of the most important psychiatric disorders: schizophrenia, mania, and depression. I suggest that these theories reflect in more subtle ways than prior examples metaphorical brain talk, or perhaps these monoamine hypotheses could be seen as sitting somewhere in a continuum of naively enthusiastic scientific theories and metaphorical brain talk. So he's getting at this idea that you have a new finding, and then that new finding is translated into the cause for everything. So, you have this new finding, and it's exciting, and it seems to, somehow explain everything. And so again, sometimes in theory, we kind of have theories that are very focused on specific mechanisms, maybe our pet projects, maybe things like that. And so, these are naively enthusiastic scientific theories, meaning that we know about this new mechanism, but we don't, spend a lot of time unpacking that new mechanism, but we already built the theory around it, saying, this is the thing that's responsible for the disorder. And in a way, that's a metaphor, because you're using that as basically the explanatory mechanism. You're saying that there's something that you can show is maybe, involved in dysfunction if you have less or more dopamine, say, for example. And that is sort of the, sets the gain for your theory, right? So this is, again, and you'll see this again and again in brain science, because, again, we're uncovering things, and they're very complex systems in play. And when you have hyped things, and this is the same thing in machine learning and deep learning, you might have a new model, or you might have a new approach, and those new things then maybe are the best thing ever, or explain the most data, at least until you really kind of spend time unpacking it and examining it. Okay, so this is kind of thinking about how new findings can be sort of grist for this mill. So these kind of theories and these kind of metaphors are grounded in solid basic neuroscience and have support from pharmacological studies and mechanisms of action. However, trying to clarify disease etiology through the mechanism of action of pharmacological treatments is deeply problematic and illustrated by the now common phrase, headache is not an aspirin deficiency disease. So you don't describe headaches is because, because you don't have enough aspirin on hand. There's a cause for a headache. Aspirin will take care of the headache for a little while, but the headache is not caused by less aspirin. It's just that aspirin is a thing that can, help you with your headache, reduce the pain, but still, the headache is still there. And the causal mechanism has actually nothing to do with aspirin. Given the more than 100 neurotransmitters in the mammalian brain, the plausibility that dysfunctions in the first three can be traced in the brain cause the major psychiatric disorder strain to the breaking point any sense of credulity. So you can't just say that like there's one causal mechanism that's this brand new thing, and we should just focus all our efforts there. Unfortunately, sometimes that's the way people act, and this is a thing you'll see in the literature. People just focus on this one finding, and really propose, okay, we should really focus resources on this one new thing. So this hurts us in terms of developing, oftentimes really strong, solid, you know, integrative theories. There's this tendency to chase the shiny object. Okay, so that's kind of talking about that. So why brain talk? Metaphorical brain talk has arisen out of a foundational feature of our profession. Psychiatry began and remains a profession that treats disorders as major clinical manifestations of our mental space. So we have symptoms, we have resulting signs and distributed behaviors. Okay, so you have to think about sort of the behavioral space of this. It's very subjective in a lot of ways, and very hard to characterize with mechanisms. But we are also a medical specialty and consider our association in medicine central to our mission, professional identity. So most other medical specialists have organs of special focus. So ophthalmologists focus on the eye, cardiologists focus on the heart, so forth. In the first decades of the late 18th and early 19th centuries, psychiatry, for quite logical reasons, chose the brain. But some 80 years later, neurology has begun to develop and took with it all the diseases where, given the methods of gross and historical pathology that had been available, one could track these disorders back to definable brain or nervous system lesions. So, psychiatry developed before neurology. Neurology kind of took that space of like physical problems with the brain. And so now psychiatry needs to have this also appeal to the brain and make explanatory statements about behaviors, and so they can trace that back to the neurology, but they're not quite making that connection between brain and behavior. And so that's kind of maybe where a lot of the problems here lie. It's a unique problem to psychiatry, I guess. Of course, with neurologists, at least the way that this is classified, we have neuroscience now, which incorporates a lot of this, or psychology departments often just have all sorts of different specialties kind of in the same place. There isn't so much that distinction anymore. So this is a quote here. Ever since the beginning of psychiatry, metaphorical brain talk has, as part of a professional conspiracy to believe, helped our own self-image as a poor relation in medicine and given us plausible metaphors to communicate about the disease we treat with ourselves and with our patients. This conspiracy, I suggest, was further reinforced through large advertising budgets of modern drug companies. So again, the view of the metaphoric brain talk is largely negative in this article, and this is something that the author, wants to kind of root out of psychiatry, given the venue. So the end part is called "So What?" So we have a very imperfect sense of brain-based disturbances that predispose our disorders. We should not be ashamed of this. We have been working hard for a very long time on a set of problems of extraordinary complexity. Talking about our profession and our disorders to ourselves, our colleagues and patients using metaphorical brain talk is scientifically immature and ultimately disrespectful to our patients. Unless we know otherwise, we should assume that our patients want us to tell it like it is, doc, even when that means we cannot tell pretty stories about serotonin imbalances. When we describe the suffering of our patients, we don't have to dress up the descriptions of their mental anguish with problematic brain metaphors. We should tell them what we know with all the uncertainty. We should take pride in being the only specialists in medicine that have chosen to treat disorders of the mind, conditions that account for a large proportion of aggregate human suffering. We may not try to hide the large amount we still do not know about causes of mental illness behind metaphorical brain talk. So I think that's a very interesting paper and kind of approach to a lot of these issues in psychiatry. It links to computational psychiatry, and then we can build computational models that sort of bridge that gap between behavior and what's going on in the brain. But computational models can also fall prey to these problems of metaphors, because if we use a metaphor to inform our computational model, then we're just basically committing the same crime in a sense. Not crime, but in any case, it's a very good piece of food for thought. And so I hope that, like, in combination with a lot of the things going in at NeurIPS, in this article, we can kind of pull those together and come up with something interesting. Okay, thanks for attending. See you next time.